Hello everyone, welcome again to the Multiverse. Before we start, please don't forget to subscribe if you don't want to miss the next videos. The subject of today is sum and linear combinations of matrices. Okay, we are going to see that actually sum is just a particular case of linear combinations. But let's start. Okay, let's start with a question. Given any two matrices, M and N, can we define a sum between M and N? Can we always define the operation M plus N? Well, there is a quick answer, which is no. Okay, in general, the answer is no. But in some very reasonable but relevant cases, the answer is yes. And this is what we are going to study next. Okay, so before we go on with the definition, let me fix just a couple of notations, okay, that will be useful not only today, but in all the rest of the chapter of linear algebra. Okay, so let's take a matrix with real entries, okay, a M times N matrix, okay, so not necessarily a square, as we already know. We are going to denote from now on the set of all the M times N matrices by M times N R, where R denotes the set of real numbers. M here, this is the number of rows, while this is the number of columns. Okay, so this will denote from now on the set of all M times N matrices, okay, with small m and small n fixed. Okay, so now we have our matrix A and we have our set capital M. We will say simply, instead of saying let A be a M times N matrix, we will simply say, okay, let's take a matrix that belongs to the big set M times N R. Okay, it will be easier to write. It will be easier to understand. Okay, so we will use this notation from now on. And what happens when actually A is a square matrix, when small m and small n are the same? Well, in that case, we can ease a little bit the notation as follows. Okay, instead of denote the set like here, instead of denote the set as M n times N R, okay, where we need to repeat N and N twice, we can simply use this notation, okay, M small n R. Okay, this is a very common notation which will be used from now on. Well, today we won't have actually square matrices, so we will use the regular notation M times N R. Okay, let's cancel these lines, these little circles, and let's go on now with our definitions. Okay, now let's take two matrices. It is important that those matrices have the same order. Okay, so both A and B should belong to our big set that we just defined, capital M, small m times small n R. Okay, so there are two matrices of order M times N, M rows and columns. Okay, we are using the short notation Aij for the matrix A and Bij for the matrix B. So just as a reminder, okay, this can help. Let me just write it down once. Okay, for the matrix A, for instance, this means the following. this means the following. Okay, that our matrix A is just this A1, 1, A1, 2, and so on until A1n. Okay, then we go down until AM1, and we go right until the last element, which is AMN. Okay, and with B, it's exactly the same. You just replace small a with small b. Okay, so now let's go on. This is just to remind you what denotation stands for. So let's go on. So we define simply A plus B as the matrix whose entries are given by Aij plus Bij. So it's really intuitive, okay? It's exactly what we thought it could be. So it's very straightforward, I would say. And now we can just go to see an example. But we, of course, need to observe that the matrix that we just defined, A plus B, is a matrix of the same order as the matrices A and B. Okay, so it belongs to the same big set, pink, to the pink set that we defined in the previous slides. Okay, so now let's go to see an example. Okay, it will be an easy example because actually the definition of sum is easy and the example will be easy as well. So let's start with two matrices. Okay, we have the red matrix and we have the blue matrix. The red matrix, okay, as you can see, has 6 entries. They are both matrices of order 3 times 2. Let me write it down again. Okay, here this is a matrix 3 times 2. That means 3 rows, 2 columns. Okay, just to remind you the meaning if you are new to this subject. Okay, so since they are matrices of the same order, then for what we saw before, for the definition, we are allowed to build the sum. Okay, so what should we do? We take entry by entry. Okay, we take now A11 and B11, and we do the sum of the two numbers. In this case, they are the same number, so it's 2 plus 2. Then we go on with the second element. The second element will be, in this case, A12 plus B12. Okay, and it's for us 1/2 plus minus 1/2. Here, I didn't put the brackets because with colors it's sufficiently clear. Okay, so I didn't need to put brackets. It's clear for us. So let's go on with the third element, pi square plus minus pi square. And let's go on again with the fourth element, minus pi plus 2 pi. I really like this graphic. Okay, it took me 1 hour to make it, but I think it's really worth it. Now it's 3 plus 0, and the last element it's 0 plus minus 4. Okay, so now we have the big picture, and of course, again, what we obtain is let me use a different color just to stress that. Okay, again, we obtained 3 times 2 matrix. So again, it's a matrix of the same order as it should be. Okay, this is what the definition told us. And we go on with the result. Well, I'm sure if you can understand matrices, you can do 2 plus 2 equal to 4. Okay, and all the other operations, okay, are all straightforward, and we obtain our matrix. Okay, whose entries are 4, 0, and so on until minus 4, the last element. Okay, so it's really straightforward. It's a very easy definition. So now let's try to make it a little bit more complicated in the next slides. Okay, here, of course, I need to cancel my 3 times 2. Okay, so let's go a little bit further with our examples. Here we have a 3 times 2 matrix again, but our matrix B is a 2 times 3 matrix. Okay, so let me write this again, just to make sure that we are all on the same page. This is a 3 times 2 matrix, and the second one is a 2 times 3 matrix. Okay, so can we make A plus B according to the definition? Well, the answer is simple, and unfortunately, no, we can't do it. Okay, because those matrices don't have the same order, so we can't sum them up. As simple as that. Okay, this is the second example, but I want to do a last example. Let me cancel everything. Okay, now we can start. Again, let's start with a matrix A, a 3 times 2 matrix, and let's take another matrix, again 3 times 2. So yes, so if we want to sum up those two matrices, we actually can, but it's not what we want to do. Okay, so let me write down again the orders. Okay, this is a 3 times 2, a 2 times 3 matrix, 2 times 3 matrix, and here we have again a 2 times 3 matrix. So yes, we can do A plus B, but we want to do something a little bit more difficult, okay, which is the following. We want to compute actually 3A minus 2B. Can we make it? Can this make sense? Yes, it does make sense. Why? Because 3A, it's something that we computed in the previous video, okay, when we talked about scalar multiplication. Okay, multiplication of a matrix by a scalar. A scalar is a real number. Okay, minus 2 times B, we can, it's the same, so we can compute it as well. Okay, and then there is this, the sum between 3A and minus 2B. Okay, so actually, if you prefer, if you think it's more clear, we can actually write this new matrix as follows. Okay, maybe you like it more like that. This is the sum between the matrix 3A that we know how to compute plus the matrix minus 2 times B. Okay, so now we clearly know how to compute this matrix. Let's go on and let's make this this easy computation. Okay, so the first is the first member, the first element, the first entry of this matrix. It's of course 3 times 11 minus 2 times 4, so it's really easy. Okay, we first compute 3 times 11, which is the scalar product between the scalar 3 and the matrix A. Then there is minus 2 times 4, which is the scalar product between minus 2 and the matrix B. And we go on element after element. Okay, then it's 3 times 0 minus 2 times 1. Then 3 times 3 minus 2 times 0, and so on. Okay, fifth element and sixth element. So again, let's summarize. Here we have the full picture. Now, again, I'm sure you can compute these small operations, and we obtain the final matrix, which is again a 2 times 3 matrix. Okay, given by the entries 25, minus 2, 9, minus 63, 26, and 0. Okay, so this is not just the sum between two matrices, it's something a little bit different, which has a name. Okay, so let's give a name to this operation. What we just did is called linear combination. Linear combinations are very important in linear algebra, and not only, okay, but especially in linear algebra and whatever will follow after. So let's give a name to this. Let's generalize in the next definition what we just saw in the previous example. Whenever we have two matrices of the same order, so m times n matrices, here our two matrices are named capital M and capital N. If we take any two scalars, alpha and beta, which are real numbers, remember, then we can always compute alpha times m plus beta times n. This will be again m times n matrix with real entries, of course, and this is called a linear combination of m and n with coefficient alpha and beta. Actually, it's coefficients, okay? And that's it for today. So thank you very much for watching. I hope you enjoyed. So please don't forget to like, comment, and subscribe. And see you soon. Thank you very much. Bye.